Picture the universe at the moment of the Big Bang, a smooth, incredibly hot plasma. Macroscopically, it is simple. Now, jump forward 10 to the power of 100 years. Heat death. Black holes have evaporated. Particles have drifted into a cold, infinite void. Also macroscopically simple. But look around you. Galaxies, stars, biology, coffee cups. We are in the middle, and the middle is chaotic. Here is the paradox. The second law of thermodynamics states entropy increases monotonically. It is a straight line up. But if the universe starts simple and ends simple, complexity cannot be the same thing as entropy. Complexity must be a curve that rises, peaks, and falls.
To solve this, we look at a cup of coffee. Pour in the cream. At the start, they are separated. Cream on top, coffee on bottom. Highly ordered, low entropy. At the end, it's a uniform brown sludge. High disorder, high entropy. Both states are trivial to describe. But the transition? That is where the magic hides. Swirls, tendrils, fractal boundaries. Researchers Scott Aaronson, Sean Carroll, and Carroll Ouellette built a digital coffee automaton to prove a specific hypothesis. While entropy marches upward, structure has its own distinct life cycle.
You might think we can just measure the information content. In computer science, we use Kolmogorov complexity, the length of the shortest program required to output a system state. But here is the trap. The most complex thing in the universe, mathematically, is a container of random gas. Why? Because it is incompressible. You have to list the coordinate of every single particle. That means a fully mixed, boring cup of coffee has maximum Kolmogorov complexity. If we used this metric, complexity would look exactly like entropy. It fails because it cannot distinguish between structure and noise.
The researchers explored the theoretical heavyweights to fix this. First, sophistication, a metric that splits data into a model versus random noise, measuring only the model. Second, logical depth, measuring not the size of the program, but the execution time it takes to run. Third, light cone complexity, calculating the mutual information between a point's causal past and its future. These are mathematically elegant. They are also computationally useless. We cannot calculate them efficiently for a running simulation. To measure the coffee cup, we need something practical.
The winner is apparent complexity. The intuition is radically simple. Blur your eyes. Mathematically, we define this as the entropy of a denoised version of the state. If you take a cup of random static and blur it, it becomes a flat gray nothing, low complexity. But if you blur the complex tendrils of mixing cream, the macroscopic shape survives. It remains hard to describe. By applying a coarse graining filter, smoothing out the microscopic details, we can ignore the random noise of particle positions and capture the large-scale pattern.
To test this, the authors built the coffee automaton. It is a simple two-dimensional grid. Ones represent cream, zeros represent coffee. We initialize the system in a perfectly ordered state. The top half is solid cream, the bottom half is solid coffee. We then let them evolve, but the rules of physics we choose for the particles determine whether complexity survives.
First, the non-interacting model. In this version, particles act like ghosts. They perform independent random walks, up, down, left, right. Crucially, they ignore each other. Multiple particles can stack on the same pixel. They drift through one another without collision. Mathematically, this is just a superposition of thousands of independent coin flips. It is diffusion without resistance.
Second, the interacting model. This represents real matter. Here, we enforce the exclusion principle. Only one particle can occupy a cell at a time. The rule is simple. Pick two neighbors and swap them. But this constraint changes everything. A cream particle cannot move if a cream particle blocks its path. They get in each other's way. Their movements become correlated. This isn't independent drifting anymore. It is a traffic jam.
We run both simulations and apply the metric at every step. First, coarse graining. For every cell, we calculate the average value of its neighbors in a G by G square. This blurs the grid. Second, thresholding. We snap the result into 3 buckets: mostly coffee, mostly cream, or mixed. Third, compression. We measure the file size of this simplified grid using a standard algorithm like gzip. This compressed size is our complexity score.
The results reveal the secret of structure. In the non-interacting ghost model, apparent complexity never takes off. It stays low and flat. Why? Because without interaction, the particles disperse into a boring, uniform fog almost instantly. But in the interacting model, we see the prediction come alive. As the liquids mix, complexity skyrockets. It peaks exactly when the swirls stretch across the cup before slowly decaying. We get the famous rise and fall curve. The peak happens exactly when the system is most interesting.
This tells us something profound about physics. You cannot have complexity without interaction. In the ghost model, every particle is an island. In the interacting model, the presence of one particle constrains the others. These constraints create correlations, and correlations create structure. The swirls in your coffee are essentially large-scale traffic jams. That resistance to mixing is what keeps the system in the sweet spot of high complexity.
This brings us back to the universe. Like the interacting coffee cup, our cosmos is governed by forces, gravity, electromagnetism, that make particles interact. They do not just pass through each other. These interactions slow down the march toward equilibrium, allowing stars, galaxies, and life to form in the intermediate stage. We exist at the peak of the curve. The apparent complexity of the cosmos is high right now because we are far from the Big Bang, but not yet at heat death. We are the swirls in the cosmic coffee.